Okay, welcome. We will just give it a minute to have everyone log in. Um, okay, looks like that we have reached a stable number. Good morning and hello. Welcome to the third Probe for EPMA Probe Image Probe Software webinar. Today we have two different topics on the menu that are that are somewhat related, and so we have two speakers, myself and John Donovan today, and we will take turns talking about these two. Okay, so my name is Anette von der Handt. I'm at the University of British Columbia. I've been using the probe software for 15 years now. As a user, I use it daily in my lab, where I run a new JOL field emission microprobe. We have a very big range of users and applications, and so I'm making full use of the different capabilities. And as I already mentioned, our second speaker will be John Donovan. He is the owner, coder, inventor of probe software. He used to run the microprobe lab at the University of Oregon, and has been now happily retired and can spend even more time improving, even though there's not much to improve, but extending the capabilities of probe software. We will talk about two different topics today. The first thing will be how to analyze beam-sensitive materials by making use of the time-dependent intensity correction function in the probe software. And then John will follow with talking about quantitative X-ray mapping and how to extract compositions, information from these quantitative maps. Okay, good. So I will make the start by talking about that, and I hope it will all work well. I will start with a little presentation. So we'll share my screen. And then continue on to show how it actually is implemented in the software, how to set up and run in the software, and how to process the data, and how it all exactly is implemented, and how easy it is to do that. Okay, so when we talk about electron microprobe, usually we refer to it as a nominally non-destructive technique. And so that's one of the advantages over other microanalytical techniques like the laser or SIMS, where we actually remove material. However, depending on the material, we actually are not always completely non-destructive. And the reason for that is that we produce heat when during the analysis, but also the electrons that hit the sample can create charging in our material. And this is usually the cause for the effects that we then see in the data during analysis. And can be a real hindrance in acquiring accurate data. Precision is often still good, but again, we want to have true accurate values. We can distinguish between just beam-sensitive materials. A lot of the biological samples tend to be quite beam sensitive. I will talk a little bit about like when does it start, what exactly means beam sensitive. We also generally see in alkali-rich glasses effects during the analysis, and in general for the earth scientists, a common problem. We have a lot of minerals that contain water or age, but also halogens, and they tend to be easily damaged during analysis. And then in addition, we have beam sensitive applications, I would say, where materials that maybe at regular analytical conditions might just be fine, but where the specifics of the analytical conditions that we need to apply can then start to become a problem. And one example is low KV analysis, where we drop the accelerating voltage to reduce the analytical volume in our sample, which the side effect that now we produce heat, we really have like a very dense electron distribution in a small material. And so there have been many reports that materials that are fine to analyze at 15 kV then can show beam sensitive behavior if you analyze them at 7 kV or 5 kV. And likewise, trace element analysis, it's one of the fortes of the microprobe method, that we can analyze minor to trace elements. And we usually have to increase the current to do that. And that often is not received well by a lot of materials. Okay. So what do we see then? Here we have plots where we look at time of analysis versus the intensities in a given material. And what we can see often is that over time, we lose or increase X-ray intensities. And if this is not monitored or tracked, of course, that would mean that if we integrate over that time frame, we would not get an accurate idea of the concentration of the element in question. And so this has been observed for sodium loss in glasses. In general, glasses are more beam sensitive than minerals. If you analyze a silicon glass compared to a quartz, a silicon mineral, you can easily see that. And the rate in these, like how fast, how much it drops, as you can see here, is often very strongly correlated with the beam current. So the more beam current we apply, the more of a change we get. And so this is another way to look at it. Again, this is like just a simplified way. And so even small increases can have a drastic effect over time. And what we are really interested in is the composition here at time 0. And you can even see that sometimes the change really happens within the first few seconds. So that's a problem. Furthermore, sometimes we see that it not only can a change happen in the first few seconds, instead it can actually take a moment to on-ramp, have some kind of incubation period, and then change. And when you look into the ceramics and glass literature, of course, they were very interested in that. You find various studies that look at that and see that the relative proportion of certain elements can extend and decrease these kind of incubation periods. And not only the absolute concentration, but also which specific element. So not all alkalis are have the same effect in this sense. And so what you take from that is just like, depending on the material composition, we can also have an effect. So it's not only the analytical conditions, it's also the material conditions, the material composition that creates a problem here. So overall, when we look at it, it's like the changes in X-ray yields are complex and not always predicted easily. It depends on the sample, as I said. It depends on the analytical conditions, but it can also depend a little bit on the sample preparation, where people have been experimenting with different types of coatings, metal coatings versus carbon coatings, and also the thickness of the coating can make a difference in kind of acting like a protective layer, can remove some of the heat, for example, like people suggest using silver coating for biological samples because it has the highest thermal conductivity. So there are ways to counteract it a little bit, but sometimes it's just, you just have to roll with the punches. And originally, in situations like this, the recommendation was to just analyze very quickly for just a few seconds to have as minimal effect as possible. Or they recommend to be as low current as possible with a widened beam. And while these are all good suggestions, the problem is, of course, that it either impacts our precision that we can achieve. Our statistics are not very good if we run for very short time analysis times and very low currents. We usually use the microprobe for the high spatial resolution, so having like very wide beam diameter is counteractive often to what we are looking for. And so back in the 80s, already there was the suggestion that you just track and monitor and correct this change. And so the idea is that usually we acquire the data continuously for the time and then integrate it and create a counts per second per nanoamps value that we compare against a standard. But instead of integrating the entire analysis time, we break it into individual intervals. And then by having these intervals, we can sort of track and monitor and apply corrections to it so that we can just determine the intercept value at time zero for the data and use that then to quantify our data. So again, like if we just do an integration over it, we would get very different values, specifically for very beam sensitive samples. But by following with the individual values, we can extrapolate back. And so this is where the probe software comes in. It has built-in functions for spot analysis. We use probe for EPMA, but we can also apply it for X-ray maps. And I will talk about that in the second part later of my talk. So I will focus now just on probe for EPMA. And in the software, we can define the number of intervals, and it records then all the data, and then the software has 3 different fit methods to the data that we can apply. And so we have log linear change, hyper exponential change, and then a double exponential function for it. And again, we have time versus intensity. And I don't know how easy it is to read, but essentially this is all the same material where I just changed the beam diameter during the acquisition. So all these were acquired at 15 kV and 20 nanoamps, and I get a double exponential function for a focused beam, a hyper exponential one for a 10 micron beam, and a log linear for 20 microns. So the same material, just depending how we analyze it, can exhibit different curves. But if we can then find conditions that fit well to one of these fitting methods, we can get a really good interpolation back to zero. I will also show that in a moment, but it's overall very simple to set that up in the analysis. There's a dialog where I can choose either normal acquisition, which means no TDI, just the integration. And then we have a self-calibration and an assigned calibration acquisition mode. Okay, just to show some examples why that is worthwhile, and what specifically the self TDI can be useful. This is an appetite that I analyzed, and what we can see here, appetite is one of the worst offenders with that, specifically as the curves. It can really depend also on the crystallographic orientation, what we get. And so here, two analysis points from here, where on once I have a relatively flat curve, and then I have a drop, and then in another part of the phase, I get like a strong drop at the beginning, and then an increase, and then it goes down again. So it's difficult at times to just assume like, oh, I know I lose like 20% of my intensities and I just apply that correction to every single analysis, because it might really differ depending on all kinds of effects that are happening. One thing that I also want to show is oftentimes people are really only focusing at the alkalis and the major elements. And while those are, of course, are very, very important, during trace element analysis, I mentioned, we can also see these effects, and they can affect elements that are usually not being seen as volatile. However, during a trace element analysis at a high current, we often really damage the material. And because when we are doing trace elements, we're only a few counts above the background, and our background depends on the mean atomic number of the material. Because we then damage the whole material in the way that we dehydrate it, or again, we move volatiles away, we can see an effect in the trace elements. So here are two examples for very hydrous, very beam-sensitive materials, a lawsonite and a phengite, and we're looking at the chromium intensities during the analysis. So chromium, usually no one ever thinks about that chromium could be an element to monitor, but we have, like, during the analysis, because we damage the overall composition of the material, you see that I get an increase in intensities, probably because my mean atomic number increases due to devolatilization, but it's a 20% increase. So not tracking that and not correcting for it, I get a very large error in my accuracy on the data by not having that corrected for. Likewise, the phengite, we get a different curve, but also an increase, and it is like a 4% change in the data. So these were the reasons why you should always do it on each point, but sometimes materials behave similar if they are if we are on the same grain. So if you do a traverse, tracking it for each individual point can be time consuming. TDI analysis take a moment longer because we usually have to wait for the detector to read out the intensities for each interval. And so what can then be done in the probe software is having an assigned TDI where you acquire a change during for one spot in the material, and then you can apply it to the other parts in the traverse. And so this is often done for, like, this is monazite dating, where you again have to use high currents, but you want the high spatial resolution. And so this is like, again, for something for traverses on the same grain, where it's likely that any kind of change is similar across, and mostly the trace elements change is the best method to go forward. And then when we do that, the way it works in the software is that it takes the intensities, it corrects them first for the TDI effects, then all the other corrections are happening, background, spectral interferences, elements by difference. Then it's run through the matrix corrections, and then it's going into an iterative loop if needed. And if it's happy, it can output the results. Okay, so that's what I wanted to show. Now I want to show you how it actually works in the software. And let me share just the screen. Okay, so you can now see my screen. So setting it up in the software is very, very easy, very straightforward. We can just make a TDI test new. Oh, yeah, okay. Well, let's save it somewhere else. Um, uh, File, and then I can load in an existing file I can load in a setup from a different from a different folder, from a different file. And okay, so let's go here and do that. I don't know why it's doing that. Okay, classic thing, should have checked it anyway. Let's do it instead of just by hand. Okay, so anyway, so I add some elements for my analysis. And so just 3, that's enough. I can define the conditions at which I want to analyze it. I can add some standards. Reload standards, so I have some standards applied. And the main thing then is that here under special options, this is where I set up if I want to have TDI or not. And so as I showed, there's normal acquisitions. And then if I want to do self-calibration TDI, I can just select that. I can define how many intervals I have. My default is 5. I actually would always do 10, 7 to 10. I found that 5 is not enough. And I can, if you want, I can talk a little bit more about strategies there. And then I have also the option to acquire TDI on standard samples, because if I have similar, usually standards should not be beam sensitive, but if we use something like an albite for sodium and whatnot, it might be. And so if we correct our unknowns, we should also correct our standards. So I can have that automatically selected. And so the time per interval is then whatever total time I set up in my count times. So if I analyze for 20 seconds and have 10 intervals, each interval is 2 seconds. So that's the way how that works. And that's it. That's all I need to do. And then I can just start acquiring and it will do that. Okay, so what happens now if I've done my analysis and I have data? Oops, that was actually the wrong one. Okay, I don't know why that all of a sudden I had that all open earlier. Let's just open that again and in processing mode. Uh, it's the MDB. Okay. Okay. Good. So now there are two places where you can look at your TDI curves. One is simply in the Analyze window when you go into standard assignments and click on the respective element. For all the analysis under this unknown, I can just here on the right-hand side look at and assign display TDI fits or not. So I can switch between different types of fits and can look at it. So log linear, log quadratic, log log. It's also where I can assign my assigned TDI correction and so on. And here on the right-hand side, it actually shows me immediately what has been assigned. Now, if you go through a lot of data, that can be annoying. And so instead, under Run, you can go into display time-dependent and alternating on and off intensities. And this opens a dialog where all the data is being shown, and I can just go through it again and again for a specific element. I can switch to an element and then go back to the points and go through all of them and see how it does. I can look at and apply how the different fits are. It shows me the goodness of the fit, the calculated intercept, the percent change it does. And in this dialog, I can also assign the fit to the sample. So usually my workflow then is just like to apply or remove the TDI corrections and then go through each analysis and find the right fits for them. And usually if it's normal analysis, iron or something doesn't really ever show it unless it's like trace element analysis. Although you see here when it's really aggressive, you see it. And in my experience, if it doesn't show anything in the sodium or whatever is like a major element volatile, none of the other ones do. But it's still useful to just quickly go through and see which one is there. And then one of the advantages of the software is like you don't have to apply a correction. You can just remove it. So oftentimes it's just a tool to monitor and not necessarily then apply the corrections if you don't find it. And I would say like don't correct if there's not a real change, because that just introduces like if you just have some counting statistics error, and you can also have it shown with error bars. It applies a correction, but this is just counting statistics. And so don't correct that, because then all your data is just a little bit like a random error applied to them. But yeah, it's very easy to look through the data with that and micromanage that. And then in addition, when you export the data, there is among them the possibility in specified custom output what you want to export. There is TDI correction percents and TDI fit deviations. I always, at least for myself, export that then as well, because I just want to make sure that I was like consistent with it, didn't forget something, but also it's sometimes easy to see if there's a total outlier, and then to maybe go back to that specific entry and see like, is that actually a meaningful, did I do the correct thing, or should I have used a different fit or whatnot? So many ways how I can track things and look at them and see, yeah, how the goodness is. And with that, I get very good results in general. And I have the conscience of mind that my data is accurate, but also I can still, if need be, do smaller beam diameters and or higher currents in general. And like tips and tricks, again, don't shortchange you on the intervals. But the other thing that I found is always just test first. Like, do you get a good curve, essentially? Like, don't the biggest problem that I sometimes see is that what people still do, like the old school, like, oh, it needs to be low current and very short. but then want to combine it with TDI corrections. And so you end up with something that is sort of beam damage, but not quite. You're not getting a good fit to the curve. And then it can actually be really helpful to be more aggressive in your analysis, actually increase the current, lengthen the time, as long as you get then a good curve that can be fit and corrected with small errors and all that. So you get more accurate data, but you also get more precise data. And what's not to love about that? Okay, I essentially took up my entire time, but pop something in the chat or in the Q&A if you have any questions. And I can also reply to questions while John is talking. Oh yeah, and one thing that I should also mention while people enter questions is that one thing is really like important, that the TDI corrections are part of the corrections before the matrix corrections, because if you have a 20% change in your composition, that affects your matrix corrections. So doing it afterwards in a spreadsheet by just then adjusting one element or so, it can be a problem with accuracy. Okay. Okay. Yeah. What is the reason for 5 TDI intervals being not enough? It's just my experience for 2 reasons. It really depends, though, how well the material behaves. Like if you get like a nicely fitted curve in 5, by all means use 5. But I've seen data from elsewhere where people used like 2, and well, you always get a fit with 2, including if you just have an accuracy. And if you interpolate back to 0, it's specifically if you have shorter intervals, it can be really helpful to have more, because it really reduces the kind of goodness. It improves the goodness of fit, because of course each interval has also counting statistic errors. And so if you have a very large error for each interval, if you have more intervals, it can do a better fit. You might say, well, then I just increase the length of the intervals, but that can be then a problem with the curve. So to an extent, it's all just like test it with your conditions, test it with your, like before I set off analysis, I just do one spot with the TDI and see like, oh, does that work or not? Because then usually you have like a pretty good range there.
I'd also like to emphasize the point you made, Annette, about the being aggressive with your analysis and your beam current. And one of the things that Annette pointed out to me some time ago is that you saw in one of her early slides, there was this incubation period where there's maybe a flat response, and then all of a sudden it starts changing. And that's, I think, the consensus, I think, is that if the sample doesn't get heated up quickly enough, then the ions cannot become mobile fast enough, soon enough. And so if you start counting at right away, then you're going to get this. You're going to over extrapolate or under extrapolate your trend. And in fact, so that's why we added this incubation period in the software, so you can actually have the software remove the Faraday cup, wait n seconds or whatever it takes, and then start counting the TDI curve. But the other way to relieve that is, as Annette pointed out, is just increase your beam current, and then the sample heats up quickly, and you immediately get a TDI effect. And so it becomes a more reliable extrapolation to 0 time. So yeah.
And I should also mention there is during the acquisition, in the acquisition options, an option to apply an incubation period, so it doesn't start acquiring it.
That's what I'm saying.
Again, yeah. So if you really are after the curve, that can be useful. And in the acquisition, in the analysis options, there's also a weighing factor, how you can weigh the first points of the analysis of the intervals, where you can weigh the first intervals of your curve more than others. So it's really the fact that I can see and adjust things as needed is, to me, really doesn't turn it into a black box, but makes it very transparent. And if a reviewer would ask or a user would ask, I could always like point to like, here I did it, here I didn't, and that.
I see you got some questions in the Q&A, so why don't I take
Yeah.
over and the mapping,
Yes.
and you
Yes.
do the questions, and
Good.
then Annette will speak further on this topic
In
after my
mapping,
talk. Yeah,
and I will also show an example of
great,
where it was important. Good.
cool.
Handing it over to John Donovan, and he will talk about quantitative X-ray mapping.
All right, everyone see my screen? Okay,
Yes.
great. So yeah, that's it. My Barbara was asking a question. So here's the three software applications that Annette showed at the very beginning. The Probe for EPMA, called Probe.exe, and that's basically the main program. It does everything except X-ray mapping. And then there's ProbeImage that does X-ray mapping. And then basically the CalcImage software, which comes with Probe for EPMA, that uh, uh, takes the standardizations and the sample setup from Probe for EPMA and combines it with the maps that were either acquired with ProbeImage, or you can acquire maps with your OEM software, Joel or Kamika, and then convert them. So if you're acquiring maps with ProbeImage, you will go to the setup acquisition window here, and you will have a list of samples and setups. And of course, you can only do up to five elements at a time, or depending on how many spectrometers you have. But then you can combine multiple spectrometer passes to create any number of maps per sample. And you can also do replicate maps, which is what Annette will probably talk about later in terms of the TDI applied to maps. So where we do, instead of doing a TDI curve for every point, we do a TDI curve for every pixel. And it turns out that we do that by replicate frame maps. Okay, and then as I mentioned, you can also convert the Joel or Kamika OEM map files to the ProbeImage format, and then you can quantify them. Okay, so let's go to my PowerPoint here. And this was all published a few years ago in American Mineralogist, how to do the quantitative mapping with co-authors, including Annette. And you can look that up if you like. It's actually a pretty easy to read paper and a lot of fun. So basically, let's go back in time now to the early days of the ancient times when I wasn't so gray. And we didn't have any quantitative mapping. And the only way we could do it was we could basically acquire lots and lots and lots of single point analyses and grid them together. And so here's an example. This is from the Martian meteorite. And so what we have here, this is a backscatter map, and you see the little dots here. Those are individual analyses acquired in Probe for EPMA. And in fact, you can still do this today with Probe for EPMA. Each point here is a single analysis. And that means you could do the full on-peak, the off-peaks, TDI, whatever you need to do. You could do it all as a single point analysis. And then using some kriging software or gridding software, excuse me, you can then translate those intensities into quantitative maps, because of course they're just single point analyses, and we know we can do quant on single points. And then this is some more examples of that for some trace elements here, and then some sulfide and maps here. So that was very, very time consuming, but it worked. Okay. In fact, I think each of these took like maybe several days, or if not a week to do. I think, in fact, this ran during a conference while I was away. Okay, so why do we want to do quantification? Well, it's because it gives us information. And if we just look, if the raw intensity, were enough, then we would just look at raw intensities and we say, whoa, oh yeah, that composition. Well, no, we can't look at this data and understand what this composition is. Once we quantify it, though, however, you can immediately recognize what mineral this is. But the raw data isn't that helpful. I think, we really shouldn't think of qualitative maps as being anything useful other than some general idea, map viewing, not map quant. So and not only is it not even maybe good for trends. Here's an example from Annette, looking at I think an iron titanium oxide, and here she's looking at oxygen, which of course is an element that is somewhat problematic to quantify, but it can be quantified. and this summer we'll all go to a conference and learn about how to quantify light elements. But here's an example of a raw data map of oxygen on this sample. And you think, oh, yeah, there's where, look all where the oxygen is, and that you would be forgiven for thinking that might be the case until you quantify it. And then you look at the map, quantify it, and you realize, oh my gosh, it's completely different than what I thought. So it is very easy to be misled. Once we do quantify these maps, however, now we have all kinds of useful information. And we can extract these maps, we can do phase identification, we can do all kinds of things once we have quantified each pixel. And that's what I want to talk about. Oh, so let's just talk about why we want to quantify it. And I'm not going to read these. You can read them yourself. And this talk will be made available on our EPMA user forum in a few days, if not sooner. So yeah, so we really want, we don't really want to rely on just the emitted intensities. We want to do a background correction, we want to do a dead time correction, we want to do a matrix correction, we want to do interference corrections, we want to do TDI corrections. We want to do all the corrections that we normally do on points, and we want to do it for each pixel on a map. And so some people have said, oh, we can use calibration curves. Well, the if calibration curves were so good, we would do them for points. And except in very, very rare circumstances, calibration curves don't really work very well on points. There is a calibration curve in ProFreePMA, and you can try it out if you like, and you will find out that it doesn't work as well as you think. And especially for things like traces, which are very background dependent, or interferences. So, just and even worse than that, just because you think you have a material with a similar intensity, that doesn't mean it's a similar concentration. As we all know from the physics, it's very nonlinear, and different, even the same intensity in different phases can represent different concentrations. Okay, so and just to kind of belabor the point, I'm going to just say, here's an example of a calibration curve. It actually isn't too bad. This actually looks pretty good. Okay, this is magnesium, K alpha in a few materials here, as you can see. Not too bad, but if we look at silicon, it's not so great. And in fact, if we look at the errors, we're talking between 10 and 25% errors. So this is not uncommon in any material. So these kinds of errors are not something you want to tolerate. Okay, so the solution is, of course, to treat every pixel as though it were a point analysis. And that means we do everything we do to a point, to a pixel that we do to a point. So we're going to obviously normalize for integration time, normalize beam current, dead time, beam drift, standard intensity drift. We standardize before and after our maps so we can get a drift correction there. We do the background corrections, including some of the very advanced background corrections. We do the matrix corrections and interference corrections. And optionally, we can even do area peak factor corrections for light elements or time-dependent intensities for beam-sensitive samples. And here's a schematic from the paper showing this, and Annette showed a simplified version of this. And the only important thing I want to mention is that there's actually two iteration loops in the software. Yes, the TDI correction is done here up at the top. Well, let me show you that. Yeah, up here. This is the TDI correction right here. And then we will do the background correction and the interference correction, all that kind of stuff like that. And if it's an MAN correction, and we iterate that. But then we also go into the matrix correction and we iterate that. And it's actually a double iteration loop. We're actually looping through this two different ways. And so with a modern computer, though, it goes very fast, so it's not a problem. And once we do that, we get, voila, we get quantitative maps. And most importantly, we get a totals map. And this has been said before by many others, but yes, a totals map is just as necessary as we have totals for point analyses. It's not the end of the road, but it is a very good indicator of whether we are at least in the ballpark. So yeah, you want to have your totals map. And I will just kind of demonstrate that now with some software. So I'm going to run CalcImage here. And this is where we've now taken the sample setup from ProFreePMA and the standard intensities from ProFreePMA. Although I should mention there is a mode in and this is where you can create a new project. It basically just walks you through the process of creating a new project. But if I and I can show you that it's actually very simple. We say we like to create a new project. based on an existing project, which means you just specify new image files. Or you can say, no, I want to create a new project from scratch. And so you very simply, you go find the Pro for EPMA file that you want to use. And so I'm going to go here, and here, and here's a map that I'm going to load in. And now it says select the sample setup. So this is the same setup you use for the standardization in Pro for EPMA that you're using for your maps. And it could be the last unknown. If you use quick standards, they might not have all the elements there, but in this case, we ran the same elements on the standards as on the unknowns, so it doesn't really matter what I pick. So I'll just pick that, and it says select one map file from each mapping acquisition. So I could pick one map per 5 elements. So the first 5 elements, and maybe the next 5 elements, the next 5 elements, so that way you can do n numbers of maps and quantify them all at once. So in this case, I'm just going to do a very simple process of looking at one map, one pass. So it's just going to be 5 elements. And in this case, we did off-peak maps and on-peak maps. This is the on-peak map here. And then the off-peak map, M is minus, P is positive, offsets. And so I'll just select one of these maps. I click open. And I say, if I had more maps to do, more elements, then I would load in another map from that set. And I click cancel at this point because I'm all done now. And here it loads in the raw data. Here's the raw data maps. And it now tells me that I would need to go to this project specify quantitative parameters menu to assign each map to each element. And typically what I like to do at this point, you can see that the off-peak maps you can see some of the compositional effects, the effect of average Z here. But what we're mostly interested in the quantification at this point is we can close the off-peak maps and we can see the on-peak maps, which is what we really care about. And if you look here, the Z here is in counts per second right here. And now what I'm going to do is I go to this project menu here. And I can see that it's already assigned the maps automatically. I can do a totals map. I can do detection limits, analytical sensitivity, atomic percents, whatever I want to do. I can do that. You can all get a lot of calculation options you have in Pro for EPMA. So there's lots of different things you can do here. And then I can quantify the map. And I just click here, calculate quantitative images, and I'm going to say, okay. And this will take a few minutes. And I'm going to open up a little window here, a little log window, and you'll be able to see the actual quantification occurring right here. And there's the total column here on the right. But if you notice, it's a little slow because it's updating this log window. But if I close this log window, you'll see it run a lot faster down here. And so this is going to take 4 minutes for this map. But I'm not going to wait 4 minutes. I'm going to cancel. And I'm going to close this project. And I'm going to open up the same project because I've already quantified it. And
John,
yeah.
1 minute.
Okay. And here you can see this is the raw data maps. I'm going to close them all up again and open just the quantified maps for that already. And here are the quantified maps. And you'll now notice that the Z value is now in weight percent. And this is the total map right here. You can see the totals are close to 100. The Z is close to 100. And then I'm going to do something really quick just before I take a break here, is I'm going to export these files to our scripting software, Golden Software, which right here. I'm going to say create some beautiful presentation output. I'll say yes, run that, and it will take these maps and run a script, and you will see that here. And so it's basically going to load each quantitative map along with a weight percent scale bar there. And these are saved to a file that you can modify and customize for your publications or presentations. And here's the total map right here. And I think I didn't have it checked, but you can also do the backscatter and secondary images also. All right, so we can take a break here, and I will continue after the break.
Okay. Great. Let's take a break until 11, and feel free to add questions to the Q&A in the meantime. And all these presentations will be uploaded to the YouTube channel for Probe for EPMA, and our presentations will also be on the user forum if you want to look at them more.
And we'll probably
Okay.
put the recording on our YouTube channel.
Yeah.
And that way you can watch it in whatever language is your native language in
Yes,
captions.
or slowed down or sped
Yeah.
up as needed. Okay, good. Let's take a break. Okay. It's 11. We can start soon back again. And there's John. Good.
All right, want me to start?
And yeah, so now we have the second part of John's talk where he will show us more about quantitative X-ray mapping. Take it
All
away.
right. So I think we were on this slide here. So just to make the point again that once we have quantified our maps, as you saw previously, and we have a total, we can also now calculate all the data types for that raw data map. We can obviously get our quant, we can get oxide, we can get net intensities, log weight percent. I'll show you an example there. We can get just K ratio intensities, we can get formulas, we can get detection limits, atomic fractions, and analytical sensitivities. And of course, we can even now get a TDI correction map, which I may show you briefly. Okay, so the problem is, of course, one of the problems is background with maps. And we developed this very fancy multi-point background method for point analyses when you're doing ultra trace element analyses in very complex materials, such as a monazite or some rare earth material. And it works amazingly well. But unfortunately, multi-point backgrounds is really not useful for quantitative mapping because you'd have to acquire a map at each background position. And so that just gets become incredibly time consuming. What we found instead is and 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 I want to go back to a paper we published in 2016 that points out that actually measuring the background is actually problematic. If we measure the background, we're actually getting very poor statistics. And when we do a net intensity calculation where we subtract the background from the peak, we actually add the individual variances. And when you're measuring a trace element that's close to zero concentration, the variance of the peak and the background are almost the same. So you actually get a worse analysis in terms of sensitivity when you measure the background. And so, if only there was a way to measure the background intensities without directly measuring the continuum intensities. And yes, there is. It's based on Kramer's law. And it basically says that the intensity of the continuum right here is equal to the beam current times the Z. And that actually is an average Z, and then depends on the overvoltage and the beam current. And so here you can see an example of where this is one from, I think, from our paper, which had lots and lots of materials where we measured the intensity of an element that was not present in the standard. So we know what the composition of the standard is because it's a standard, and we are now measuring at the peak position to obtain the continuum intensity for that material, and using some physics for the absorption correction and some other things, and knowing now that we actually want to calculate Z in terms of Z fraction, not in terms of mass fraction. We can actually get this curve here, which is extremely stable because this curve depends on the concentration of the major elements. And we can measure the major elements very high precision. Yeah, that's Z, is that Z. Okay, so this is just a really quick, I'm going to blast through this just to point out that by measuring these curves, and I'm sorry about the old screenshots there, but the point is that we can do this example here in the middle is sodium K alpha not corrected for continuum absorption. And then once we correct it for continuum absorption, we get a very nice curve, as you can see here. And in fact, here's a comparison looking at uranium concentration as a trace element in a material. And measured the material with off-peak backgrounds. And then we threw away the off-peak background measurements and just used the MAN background correction. And you can see we get a much better statistics. And that's just the beauty of the MAN correction. You don't need to acquire anything on the unknown, and you get better statistics. So if we can get the same accuracy or better, and maybe it's even better because we don't have any off-peak interferences since we're not measuring off-peaks anymore, and it takes half the acquisition time. And when you're mapping, time is the key here. And here's an example of where we've measured off peaks on these zircons here for hafnium, uranium, some other elements, trace elements. And then we took the same data and just threw away the off-peak backgrounds and calculated the background using MAN backgrounds. And you can see right away that we've got better statistics, okay, on the hafnium and the uranium and the other elements you can look at. And it took half the time. So what's wrong with that? We can also improve sensitivity another way. This is some apps from Aoife McFadden at the University of Adelaide that she did a while back. I couldn't find the raw data for this somewhere. It's buried somewhere. But what she was looking at some otoliths and trace elements, sulfur and phosphorus and things like that. And we all know we can improve sensitivity in our maps by increasing our beam current, increasing our counting time, but we can also do it by improving our geometric efficiency. And that's why manufacturers, Kamika and Joel, have gone to larger crystals if you want to get better sensitivity. But we can also do that with regular crystals by just using more than one spectrometer. And this is called the aggregate feature in Pro for EPMA. We do it for points and we can do it for maps. And so you measure the same element on more than one spectrometer, which is kind of a cool feature in PFE, is that you can have the same element measured multiple times. I probably should reference my titanium and quartz paper from 2011, but if you've read it, you'll know that we got a sensitivity around 2 to 3 parts per million for titanium and quartz. And if we add multiple spectrometers together and quantify it, we actually now have a better sensitivity than we had before. And you can see here we're getting down to 300 parts per million in a map, and that's per pixel. And Annette has already talked about the time-dependent intensity correction, and she's going to talk about this more. So I'm just going to point out that you can see some weird effects. And this is an effect that was first described to me by Ben Hansen at Corning Glass, where, of course, they're famous for a Gorilla Glass, which is in all our cell phones and laptops and things like that. But we can get this weird effect, and this is a constantly scanning beam. It's not stopping anywhere, but we're getting these little weird kind of gridding effects here. And it's actually a TDI effect. And it has to do with the way the ions migrate while the beam is moving. And you can imagine the beam is moving and dragging along some alkalis because of that subsurface charge that is moving under the surface. And if we quantify it without the TDI correction, you can see that we still get the same a pattern here, even though it's quantified, okay? And it's true for the potassium and the sodium. But if we now in here, this is kind of was it just a serendipitous thing, but there was a sample here that was not beam sensitive in the corner here, right here. And so the map, this is each replicate map. We did 5 replicate maps. You see the sodium intensity is dropping and as the TDI effect kicks in, because interestingly enough, as this may seem unbelievable, but this is a map here. We're talking about 18,000 seconds here, okay? And the pixels down here at the bottom are the quartz, so they're not really changing, that's just noise. But the ones up here are the sodium signal, and the slopes varies depending on where it is in this melt inclusion here. And when we quantify it, though, we get a perfect correction. And when I first saw this, I couldn't believe it. I think, how could it possibly be so good? But it is. And so both the sodium and the potassium are not perfectly corrected for the TDI effect in a map. All right. And then you can even, like I mentioned before, you can even show the percent correction for each pixel, which is kind of wild. And this is just a synthetic glass. I won't even show it again, but we can actually get exactly what we think we should get. We can also do interference corrections in maps. And so here's an example of 2 sulfides, okay? And you can see that one has more sulfur than the other. And so you might guess at what those are. And if we look at the molybdenum map here, as we all know, there's a large interference of sulfur on molybdenum. And you might think here, oh, we've got like maybe, 1.8% molybdenum here, and maybe, what's that, greenish yellow, 1.3% here, and this little phase here has almost no molybdenum. But in fact, if we apply the interference correction, you'll actually see that the molybdenum concentrations on both phases is essentially 0. And it's this phase right here that is the molybdenum-rich phase. So you have completely misapprehension about where the molybdenum is in this material if you didn't do the interference correction. So do the interference correction. And by the way, the interference correction needs to be done as part of the matrix correction. This is why we have that double iteration loop. Very important. And so I'm going to just really quickly demonstrate that for you. We'll go to CalcImage. And we'll open up that project. And webinar 24, and here's an interference test. And then I did it. And the cool thing, one of the things you can do with CalcImage is you can make a copy of your raw data and you can process it in multiple different ways. And in this case, I processed it without the interference correction. Okay. And that's this project here. And if I open up, if I close all these images here and open up just the quant images here, and you'll see that this is the molybdenum, right? Where's the molybdenum here? Yeah, this is the molybdenum on here, and you can see that and this is flipped around because this is in joule units, whereas the image I showed you before was in Kamika units. But you can see the difference. The Z here is like 1.9, and here it's like 1.2. So now if I close this project and apply the interference correction, which, by the way, can be specified in ProFreePMA ahead of time, or you can just do it in the program here. I'll show you that. So here's the close all the images, and I'm going to go to the assignments here, go to standard assignments. This is the same dialog box that's in ProFreePMA, and I'll click on molybdenum here, and you can see that we've said that this is the molybdenum standard, it's molybdenum metal, and we're saying the interference correction is pyrite for sulfur, and it's a first order interference. And you can actually model this here. You can actually see that sulfur, yes, is a big interference correction in for molybdenum. And we can assign that. And now you see the molybdenum here actually it works both ways. The sulfur is interfering with molybdenum, but sulfur also interferes with molybdenum. But of course, it's the interference of molybdenum on sulfur is essentially zero because it's such a trace amount. But I put it in there just to be rigorous because ProFreePMA can handle self-interferences where two elements interfere with each other, like titanium and barium, or arsenic and lead. So it's kind of cool. And the reason we can do that is because, of course, we do an iterative correction on the thing. And now if I open up my already quantified, this is like Julia Child pulling the thing out of the oven. And you can see here now our molybdenum map, and the Z's are all essentially noise. And this is our molybdenum rich phase here, which actually has about 0.14 or 17 weight percent of molybdenum. So that's pretty cool. And going back to our talk. So yeah, so I'll just show that again. And there's our molybdenum rich phase that we would not have known without the interference correction. And also, this is kind of a point that Anette has made on the forum, which is no more rainbows, because it can be very unintuitive, interpreting what's a high and what's a low, depending on if your rainbow has black on both ends, which this one doesn't, fortunately, but it can be problematic. And in fact, it also is just psychologically in terms of the interpretation. So this is iron in a titanium implant, I think a surgical thing. And if we just change the palette just a little bit, we can bring out a completely different effect. So the palette choice does matter. That's up to you, but it's important to emphasize the things that are important. Hot pixels can really obscure data. So here's an example of some maps on quartz that I did for Australian National University a while back before they had their ProFreePMA software. And you can see the hot pixel right here. You see that pixel right there, and there's some pixels right there. Here's a hot pixel here. There's a hot pixel there, here, there, everywhere. And if I display this in normal weight percent units, we don't see anything interesting. But if I display the same data in log scale, all of a sudden we get all kinds of amazing detail. And that's because the hot pixel no longer dominates the palette here. And so this is in log weight percent, just pointing out some mapping things. And in fact, you can actually see really subtle things here where you can actually see secondary boundary fluorescence effects in the log scale, which you wouldn't see in the normal map. And so this is a boundary effect from secondary boundary fluorescence here, which is kind of cool. Okay. I think I'm going to show one more thing in the let's see, let's go up here. There was one thing I skipped, probably 10 things. So I'm going to open up another project, existing project. Let's see, conclusion. Well, I could show the melt inclusion here because it's a mapping thing. So here I did, and again, I made a copy of the project where I applied the TDI correction and where I didn't apply the TDI correction, just to show the difference. And so I'm going to open up the project here with the TDI correction. Here's the raw data. We can all see, and by the way, these maps are done with the mean atomic number background correction, and you can see the mean atomic number background correction in CalcImage just as you can in EPMA. And so here's the correction here for sodium. If I turn off the continuum absorption correction, the relative percent deviation goes from 6 to 11. So you can see the importance of performing an absorption correction for each mean atomic number background. The numbers here that you can see, whoops, the numbers, let me zoom back out. The numbers here you can see, whoops, I'm not in PowerPoint, I have to remember that. The numbers here you can see are the standards down here. And then here's for potassium, and pretty good fit for potassium. That's what the absorption correction. Aluminum. And the idea here, by the way, just in case it's not, you notice that some of these materials are not selected, and that's because, of course, this is, say, the magnesium here, K alpha, but you obviously don't want to measure magnesium in magnesium oxide to get the background, because you won't get the background. And in fact, even in some cases, you could say, I'll select this halogen, this apatite, and I'll update it here. And you'll see that it's an outlier. And why is that? Well, it's because calcium second order, is it, or third order, interferes with magnesium K alpha. And the cool thing about this curve is that when you get these curves and you look at them here, if the point lies above the fit, and it's always going to basically be above the fit, unless there's some very abnormal absorption edge effect. But generally, whether it's an interference, which in this case, the 285, the apatite is, or it's a contamination, then that point will lie above the trend. And so you just deselect that with a control click and click update fit. And now we get the proper fit. So the good news is that you don't need to know if it's an interference or a contamination. It will lie above the trend, which is why you want to do 3, 4, 5, 6, or whatever points on your standards. The good news is that if you measure the intensities on your standards as primary standards, you can also use those same measurements as intensities for the mean atomic number background curve and for the interference correction for that matter. So you don't need to actually make any extra measurements in general unless it's an unusual case. But this takes, a few minutes as part of your normal standardization. And then once you've done this, you never have to measure your backgrounds again for your unknowns. So that's kind of convenient. Anyway, so when we go to the quant now, and so this is the raw data, and so I'm going to close this up. And here's the raw data here. And by the way, I should point out that you can also do any of these. You can do oxide, you can do whatever you want. If I open the oxide images, here's the same data now, corrected for TDI, but now it's in oxide. And one of the things I want to point out also, and in fact, so this is the total image here, and it's 100% because I did water by difference, okay, because it's a melt inclusion, and I wanted to see what the water content would be. And so this is the water by difference here, and you can see it's about, it depends, it varies, but it's around a few percent in this melt inclusion here. You want to average pixels, obviously. In fact, we should probably do that. I could show that. I'll use, okay, I'm going to use a different project for this. But let me just, yeah, and here's the cool thing. If you don't include the element by difference, here, so I've checked here, calculate element by difference image. If I don't calculate element by difference image, but I do include water as an element in the correction, which I have because you can see it's right here. Element by difference is right here, hydrogen. And since I'm calculating as stoichiometric oxygen, it's water, then it will calculate the effect, the matrix effect of the water, but not calculate a total of 100%. So you'll actually get a real total, and you will have the water by difference accounted for. So that's pretty cool. So let me close that up. And I'm just going to leave that there for now and go back to the presentation. Okay, so now, so what I'm going to show you next in the software, but I'll show it here first, is you can actually take these quantified maps now. You can do all kinds of things with them. You can extract pixels spatially. You can make sure I didn't skip something. Yeah, okay, good. Yeah, you can extract pixels spatially, okay, like we did here. We drew a little polygon here. We can do profiles. This is digitized polygon, and we can filter for that area, and we can get the composition of just that area, just that rim or whatever we want to do. And here's a way of where we can actually say, only show me manganese concentrations between 4.5 and 7 weight percent here, 7.25 weight percent. And I don't know what this would be useful for, but you can do these kinds of calculations. There we go. And so, yes, so let me show you that in CalcImage. So I'm going to open up another project. Yeah. Okay, I'll open up this project here. Okay, so this is that one you saw earlier in the talk. So first of all, I'm going to close all the images. We don't need them open. You can have them open, doesn't matter. But we'll go to image processing now. There's a couple things we can do. One is, and this is something that the geologists like to do, you can open up that project. It defaults to this here. And you can say, let me identify the phases in each of these things. And I've already done this. It takes about a minute to do, so I'm not going to do it, but I did it already. And you can actually see the different phases here and clusters. And that just, you basically give it a tolerance, and you give it the number of phases you want to divide it into. And that's your call to make. But this is basically a weighted k-means clustering method. And it's quite good. And then once we have that, we can actually then calculate modal abundances for that calculation. And so here is the area percent of each of those phases. And if we want, we can actually define the density for each phase if we know it. And then we can even get the mass concentrations. Here I just assumed a density of 5, so it's not that meaningful. And so there, you don't see any difference between the area and the mass because they're all the same density. But if you have different densities here, you've got different mass. And this is, some people feel this mass balance calculation is very useful. And then here's back to where we have extract the pixel shapes. There's a lot of things you can do in this CalcImage software, reprocessing your quant maps. Of course, you can do all the same operations to your raw intensity maps. Well, why would you? So here I'm going to load in the quant map. And it could be oxides, it could be atomic percents. You decide what map would be most useful for you to do your work on. So here's an example of the digitized polygon. And I'm going to go here and I'm going to say, just give me, oh, I don't know, this area here. Okay, I'm going to close that polygon. It'll close it automatically if you forget. And I'm going to do something where I'm going to say, plot the polygon histogram. So this is going to extract that. And by the way, if you don't define a polygon, it uses the entire map, which takes a few minutes, so I don't want to do that right now. So here is two things. One is, here's the composition of that area, okay, with the variances. Here's the area here defined. You can save that image. And then here is what I'm kind of calling a quantogram. It's a quantitative histogram. And so for each of the elements here, we are showing where they, how they're distributed. So you can see the total is distributed around 100, as it should be. This is your iron distributed from here to here, your molybdenum from here to here, and your chromium from here to here. So this can be very useful to correlate composition with area. And then you can also, and you can change which element you're displaying. So here, if I change to chromium, I'll now get the chromium map. And I can now say, digitize a profile. I can say start, I don't know, let's see, start here and go to here. And then I can say extract that, and I can plot it up here. And now I have my map, including the total and all the elements there. And of course, you can define as many as you want, 20 points, and then you get that. All right, so this is kind of a lot of fun. People have a lot of fun with this. And this was all work that was I did with Gareth Seward. It was a lot of fun. Okay, and so let's just continue here before I run out of time. How much time have I got, Annette?
Depends if you want to live answer questions, but 5 minutes
Okay, well, you know,
without
I'm
questions.
willing to stay after the you know, the formal close and answer some questions online. So if anyone wants to hang out afterwards, as long as Annette keeps the connection open, we can do that. And I will also answer questions by typing some of them during the rest of her talk. Okay, so here's that profile feature you saw, and here's that histogram with using more pixels. And this is the modal analysis that I just showed you before. This depends on this is a different sample. This is from Paul Carpenter. And this is the modal analysis. And here you see we've used the actual densities for each phase. So we're getting area percents here, but we're getting mass percents here. And then we've also done a match ID based on a DHZ database. The software comes with not just DHZ, but also the NIST standards, the American Mineralogist Crystal Structure Dataset, which are ideal formulas for like 4,000 minerals. And ore, Dana's ores and things like that. So you can use, and you can make your own databases, and you can actually define your own match database in ProEPMA from analyses that you perform. Yeah, so you know, the idea here is just to you know, let's treat our pixels with the same respect that we treat our points. You know, let's give them everything, because here's the thing about it. You notice that when I did those profiles and things like that, I was using areas because these pixels are quantitatively equally accurate as our point analyses. What they lack is a little bit of precision, and we can get back that precision by simply averaging multiple pixels. And that is why I should point this out to you here. Let's see, where is it? Yeah, that is why. Oh, this is an old screenshot, but I think in this screenshot, this is using a standard deviation for the error bars here. But in the current version of the software, you can choose between standard deviation and standard error. And the thing is, if you use standard deviation, it doesn't matter how many pixels you you average, you're going to get the same variance, because the standard deviation is the variance on a single data point or single pixel. But the standard error is the variance on the average. So generally, when we're doing maps, we want to use the standard error. And so now in the current software, you actually have a choice between standard deviation and standard error being the default, because that's normally what you want to use. And then you will see an improvement in the precision as you average more and more pixels. So just to mention that. Okay. And I think that's it, I think. Yeah, so I really think that we should be quantifying all our X-ray maps. If we're going to quantify points, we should be quantifying pixels, and do all the corrections that we do to each pixel, that we do to each data point. And as I've mentioned before, all the corrections we can do to them. And then, you know, now we can extract information based on these spatial or compositional relationships manually or automatically. All right, and that's it. And maybe we can do some questions, I guess, or what do we got here? You want to read some
Yeah.
questions to me, Annette?
Yeah, there were a couple of questions that I haven't answered because you are the specialist for this. Um, so some were just like, did you make any maps with similar detection limits to point analysis and including for samples that are not beam sensitive? Like, did you do a direct one-on-one comparison
Do they
once?
mean, did I use a pixel counting time equal to a normal counting time?
That's how I do understand the
Well,
questions.
I would just reference that uh, map that I showed at the very beginning of my talk. Oh, I'm not sharing my screen again. Sorry. Let me share my screen again. So if you will remember, I'm not seeing yeah, if you remember on
Right.
my talk at the very beginning, I showed these maps here that were done using single point analyses. Okay, so the counting time on each point was like a 10-second, I think maybe it was like a 5-second because I was just trying to save a little bit of time. So yeah, I did a 5-second analysis, but it takes forever. And like as I mentioned before, the accuracy of the pixel quantification is the same as the point quantification. It's just that we lose a little bit of precision. So you just want to average some pixels together to get better precision, but your accuracy is going to be the same in both cases. Does that make sense?
I think so.
Okay.
Okay, I skipped two that are very specific and that you can answer in while I talk. There's another one by Hans-Peter Meyer referring to the secondary boundary fluorescence effect in the map that it currently cannot be corrected, but is that something
But
that
it
you're,
can, but it
but it
can.
can. So maybe you can
So
say some things.
so yeah, uh so there's been papers. So basically, what's happened is I do most of my Monte Carlo modeling in Panetma or which is, you know, that I should, and I think everyone here knows that you can do Panetma calculations in the standard program. Um, it's it's very, it does everything, including fluorescence of boundaries. And the Panetma is great, but it takes a while. I mean, it's not fast. Um, a better alternative, if people want, is they can get my standard software, which comes with CalcSAF, which is free, and you can go into this window here. You saw in the menu here, this one right here, and you can define a beam incident material, you can define a boundary material, and you can define a standard for the X-ray. And in this case, this is something that that Castang pointed out 80 years ago, is that if we're putting the beam into some pure copper that's adjacent to cobalt, and we're measuring cobalt in pure copper, and we do that, well, we're going to see something very strange. And it's called secondary boundary fluorescence. And here it is right here. So we're going to get a signal of about 4.5 weight% of cobalt when we're 1 micron from copper. And you can see it goes down to like 2%, or here's about 1% at 10 microns. And it goes out here, and it keeps going here. If you plot this as a log scale, you can see it just keeps going. So depending on your sensitivity, and in fact, it was in a group at Oak Ridge National Lab that contacted me because they're analyzing zinc in these magnesium aluminum alloys, and they were detecting zinc a millimeter away from the boundary, and they were wondering what was going on. So I showed them this, and you can run this calculation here. And if you do run this calculation here, the data file that you calculate from this can be used in ProPMA to perform a correction for this. Now, there's an assumption made here, which is that the boundary is infinite and vertical, okay? And if that's the case, this will work perfectly for you, although it doesn't yet correct for Bragg defocusing. So you'd want to put your boundary perpendicular to your spectrometer. so that or I should say parallel to the crystal on the spectrometer, so that as the beam moves or your boundary moves, it doesn't defocus. Think about it.
There's more on the forum about that.
Yes. Yeah.
But yeah.
Anyway, yeah, and you can model it, and then there's a correction in ProFuPMA to do this in the analyze window. You basically specify a file that you've calculated here, and it will apply it. Yep.
Okay, we're getting up in time again, but I think Valak asked an important question. What is better to use for extraction of data, average and standard deviation, or average and standard error?
Well, so I just talked about that for pixels. So I'll say this about it for points, and I've actually talked to statisticians about this at the university, and they basically go, I don't know. And it's not that they don't know what you should do. They don't know why we do it the way we do it. So typically what you see in scientific publications is people will quote the average and the standard deviation. But the standard deviation has nothing to do with the average. The standard deviation is the variance for each data point. So if you're quoting the average, you should quote the standard error, but nobody does. And when I ask statisticians, why do we do that? They go, I don't know. And the only answer I heard was that, well, it's kind of a worst case scenario, so maybe that's okay. But no, really, whenever you quote an average, you should use the standard error, because that is mathematically correct. So just keep that in mind.
Good. Okay, excellent. Yes, anything else we will do in the Q&A part or after when we're done with the presentations.
So you'll continue.
And so I will continue with a very short presentation on how to do TDI corrections in ProbeImage. John actually has, to a large extent, already talked about it, but let's still have a look at it again. Where is my... there's my presentation. Let's share it. Okay. So as you've already seen, you can also do TDI corrections in ProbeImage, and that is actually something that, at least to me, is incredibly powerful. And it really opens up the possibility to do analysis in materials that are very, very tricky to analyze otherwise, for a variety of reasons. Okay, so how does it work? It's very similar to how we do analysis on spots, but instead of analyzing different intervals during the analysis, in this case, is you acquire multiple maps. So you run the same map multiple times with probably relatively short acquisition times, pixel times, but you do it repeatedly again and again and again. And microprobes are very, very finely tuned, amazing beasts. And so usually our stage reproducibility allows us to do that even in stage mapping mode, where then these repeat analyses have the same location for each pixel, for each location on the sample. And so we can actually look at the change in intensities over repeat beam exposure, and can track thereby any kind of change if there is one in the samples. And so here's an example where you have a phase of one composition and surrounded by something else. And so when we just track 2 pixels, one in the outside phase and one of the mineral of interest against time instead of intervals, now our timeline is different maps. And so for each pixel, then we can correlate then the individual pixel intensities and plot them against time. And with that, then again, just as in PFE itself, we have like different types of fits to this, and try to see how it is. And then with that, we can quantify the data and correct for any beam sensitivity that might have affected even the maps. Okay, so one thing that's always important is like, does it actually work? And someone already asked, like, what is an impressive example of the TDI correction? And so what I'm showing here is kind of like, that was my initial proof of concept. Can I actually believe that it does all that I hope it does? And so I looked at one of the standards in my previous labs collection, which is a Corning glass A. And that glass has very high alkali concentrations, very high in silicon. And the published value is shown here. And this glass is like so insanely beam sensitive. It's really not a great standard. Because what I found, and I won't be able to show you because it's impossible to capture. It's like it's losing most of the sodium in the first like second. Like you lose 40%, I think, of the sodium in the first second of beam exposure, unless you go like really low current, really, really wide beam. So very finicky. Now, so what I've done is did exactly that. I ran multiple maps with what we call now TDI scanning. So at 15 kV and 30 nanoamp, I ran multiple maps, admittedly with a focus beam, which again is like very against what you would want to do, but very, very short dwell times. And that's one of the advantages really that but we can do that with maps. We can have like sub-second dwell times, like milliseconds, and which is something that we can't define in classical TDI. I can't say have a 1 second analysis and split it into 10 intervals. Likewise, I don't trust the detector. I found that when I actually look at the detectors, oftentimes the first second is not always correctly read out. I talked to JOL about that. They know about it. I actually found that the JOL software seems to clip the first second at often, which is not great. And so, but if you're in the mapping mode, you can do that. And so you just create as many maps as you feel you need. In this case, I did 11. And then I can aggregate them. And so I can get to a certain amount of counting statistics just by having a certain number of maps. Okay, so when I look at it and just aggregate all these maps then without TDI, what I get is exactly what I always worry about is I get like compositions that are instead of 14 weight percent, I get like 4 weight percent for sodium. And usually the silicon goes up, the sodium goes down, and I have like 1.5 weight percent more silicon in the values. Now, when I apply the TDI scanning, I actually get really great data, all things considered. Can be fine-tuned a little bit, but specifically for the sodium, I do get very close to the published value there. In addition, the nice thing is, as you can see in this is supposed to be a standard. What you can see there are all these round spots and partially overlapping. I should show you a backscatter image with it. You can't see previous analysis spots. That's the other devilish thing with this material. It's like you can't, specifically something that was analyzed before for whatever reason, you actually can't always see the beam damage just by looking at the backscatter secondary. But with a mapping, all the dark blue ones, even in the corrected value, are previous analysis spots. And you can see that they have lost various amounts of sodium. But here in the main area, that's kind of where I can now securely acquire, like export my data from, knowing exactly where it's, so to speak, fresh. And again, just to show, if I just look at the last map for sodium, if I just look at the last one here on the right-hand side compared to what I get with the TDI scanning, this is after half a second of mapping that each pixel experienced. And you can see that yeah, almost all of the sodium is gone, and the previous spots are like, there seems to be a baseline how low the sodium goes. So again, very, very powerful in the mapping mode. So to me, that really shows me that I can get accurate compositional values in something that is very, very beam sensitive. And in addition, it gives me all this information where I have potentially previously analyzed points in other samples. I would potentially have like other phases. So I've been using this technique quite a bit to look at melt inclusion, but also look at grain boundary melt pockets. So where you have not always the option to just widen your beam, like three-dimensional geometries that are not ideal for just having a round wide beam. So really, really useful. Okay, so John already showed the melt inclusion data. Again, it's very useful, specifically if you have a material where there's an element that you cannot analyze, like water. So if you have an element by difference, if all your cations need to be correct, they need to be accurate in order to get a relevant amount a correct number for this element by difference. And so in this case, there are like correction factors of up to 250% for the sodium. And so, of course, there is a bit the question like, if you really want to use things for glasses, if you want to do analysis on very solid glasses, using TDI scanning gives you a lot of control over the analysis, what you can do. And what I like in particular is like you can like add and subtract maps to your calculation as needed. Like if you find like, I want to have a slightly better error on my data, I can like add 5 maps. Or if I see like, ooh, now I get like a really god-awful fit to it, I might like, instead of processing the 11 maps, I might just process 8 maps and live with a worse statistics. So it's really powerful. And what is really nice is that it also gives you TDI correction maps in the software. So again, it's not a black box. You can really see what's going on, and you can assess if you agree or disagree with how the processing comes out, and you can spot errors. Again, here an example of before and after potassium values, and you can they're at the same color levels. And so you can see that it really does a good job of correcting the values and give you more even like a more realistic idea of the intensities. Another application where I used it is for minor elements in foraminiferous. So this is a foraminifer, so it's carbonate, really beam sensitive. And so I've done, people are interested in the magnesium-strontium ratio, and we found them to be very variable. And so I ran like maps at 15 kV and 50 nanoamps focus beam, something I would never do in a spot analysis. And you can see for the magnesium values, I get like abundances up to 2 weight%. For the strontium, I used a multi-spectrometer setup. Most of the values are around 0.2 weight%. And again, I can just use that with the scanning, and you get these beautiful maps that are so beautiful that JOL now uses the magnesium one as their email footer. So clearly they like that too. Okay, so let's have a quick look at how it works in the software. You already seen most of it, but just to if you're in probe image, okay, I just had all these things open. So again, in probe image, you just go into the setup and acquisition. And again, it's you just set up your analysis and then you define here the number of replicates. And so it's a very straightforward, simple way to do that. Not much else to do. You define your area and say how many you want to have of that. And then when you go into CalcImage, here is the glass data. And you go into quantitative parameters. When you go into standard assignments, very similar to what I showed with the point data, you have the option then when you click on the respective element to pull out the data here and visualize TDI fits. And because, of course, maps have like many, many, many different pixels, there is like a way that you can sample either every 64th, 128th, and so on and so on and so on. So, and then if we do that, I can actually see the data and can look at it and see what might be the best fit. And yeah, just in the spot analysis interface, I just then decide what I kind of want. Again, I can't necessarily always look at each individual pixel, what makes sense. Specifically, if I have like multiple different faces in my map, I might see some that have like, I might see very different fits in this window because some are specific to the beam sensitive phase, and it might be surrounded by non-beam sensitive phases. And so what I just do then is I process it maybe in one or two different ways and then let the data speak for itself, where again I can have the TDI percent error and whatnot shown, and then I can see if I pick the right values for that. Okay, good. I mean, that's essentially all there is to it. In terms of setting things up, and yeah, it's again very powerful technique if you want to analyze something where you worry that most of the change happens in the first seconds. It's incredibly powerful if you analyze something where the added geometric visualization of how intensities change, or again, if it's something that is not perfectly round, so you can't do the widened beam diameter, again, just make a map and take it then from do your polygon. If it's something that, again, grain boundaries where you have these inward sloping sizes, where you otherwise, if you have something like a small rim somewhere, you can draw that all from a map, and you don't have to correct for it if you don't see any problems. But it gives you the peace of mind that you will find any problems if they happen, and you can feel confident in your data. Good.
So, Annette, I can ask you some questions that were in the Q&A.
Mhm.
So, as Peter Meyer asks about the skipping of the first point with the Joel, is that just during mapping or points?
It's also it's actually during the points. I don't want to. Okay, so I'm still.
Is it related to the time it takes for the Joel Faraday cup to be pulled out? Have you?
I think so, but it's not just the Faraday cup. It's because it's not really consistent. It's and I see it now that I've do so much PFE TDI. I see that it just happens occasionally, and again, to me, it looks like that the very first second is coming in at like 50% of the counts that would make sense with the range. And
I think it's worth adjusting the Faraday weight out time in the
yeah,
file.
So just to say, and again, I don't have an absolute thing, and it depends a little bit also on the generation, but I went down the rabbit hole and was like sitting next to, was on something that showed it with a stopwatch and like relative to the Faraday out, and would look at the total time that an analysis would take, also between the JOL software and your software. And I felt that the JOL software was ever so slightly like shorter for the same count times than I would get on it. And what I do know for a fact was I reached out and was like, I think that I talked to Pete Maxwigan and JOL and was like, I don't know, I occasionally see that. And they were like, yeah, we see that like they have been labs that for whatever reason did like 1 second analysis. And so they do a lot of profiles, and their recommendation is usually to have this incubation period of a second
Yeah.
there. But I think it's something in the electronics, but that's to an extent why
Well,
I never analyze less than 10 seconds.
well, one thing I will tell you that I do know for a fact is that each generation of Joule microprobes has a slower picoamp meter.
Yeah.
So the original 8900, 8800 was actually pretty fast. The 8500 and 8200 were a little bit slower. You had to add about a second after you pull the cup, after you put the cup in before you tried to measure the picoamp meter current, beam current. And then with the latest generation instrument, you need almost 2 seconds, and some people actually a little bit more than 2 seconds before you get a stable beam current measurement. So something in the Joule electronics is slowing down, and I don't know exactly what it is. Here's a question. Radek asks, can we calculate ratios in the maps? And do you
Yes.
want to, yeah,
Yeah.
yeah. No, and in fact, I can actually show this if I share my screen, I think.
Yeah. It's just in CalcImage.
Yeah, yeah.
Just like you can do map math on the
So
JOL
here,
interface.
yeah, so here it is. What you can do here is what you can do, oh, and this is not a great map for this, but you can do, you can look at, you can assign colors for each of the elements. So you can say, you know, and you can say turn off copper and turn on molybdenum, and then you see a different map, you know. And you can also do image math on the maps. This is where you calculate ratios of different maps. So you can say, so basically each map is one of these variables here. So sulfur would be A, and then B would be the next element, and C would be the next element. So you can just basically calculate your image math, or you can do RGB images. So yes, the answer
Well,
is
you
yes.
can when you define the image math calculation, there's like you can select whatever map. So
Oh,
it's
that's
not
right. Yeah, sorry. I was grasping at what you're supposed to do. Thank you. Yeah, it asks you which element is each
yeah. So
parameter.
you
Yeah,
select that and then say select, and then you just click on whatever
right. You're exactly correct. Sorry.
map you want to define as A, B, and C. And so
I
you can do that quite
yeah.
and depending what type of you can also calculate stoichiometry in CalcImage. So if you want to have like a atomic percent, or if you want to have like a four-stride map, you would just pull up the respective data set
Yeah. So here I
if
can
it
do
was
iron
calculated. Yeah.
minus sulfur divided by
Yeah.
copper. I have no idea what it's going to do. Now you click calculate, and there's your formula. You got here A minus B plus C, and that's A equals iron. Yeah, so you can do it. You can do anything you want. Yep. Okay, and then Radek has got some more questions. He asked about the detection limits on the map he says typically where were the conditions for the map? Okay, the conditions for this map, I think I have it open here. I go here, and the conditions are right here. They were 100 nanoamps. I think that's what the conditions are. Is that correct, Annette? I think, yeah. So it's
No,
50.
that's from that's yes, but not entirely. That's the unknown that you pulled in.
Right.
Oftentimes it's
Oh,
different.
right.
So
So
your
here it is.
conditions are
Here it
down
is.
there, so it's
Yeah, here it is.
100. Yeah.
So it's 100 nanoamps right here. In fact, when you click on each of these elements here,
Yeah,
you'll see the map
exactly.
used for the background, the plus and minus background. So here's the beam current measured at the beginning of the map, and here's the beam current measured at the end of the map, and here's the dwell time for the backgrounds were half a second each, and for the on peak was 1 second. So yeah, so that's all, and that's how we can do a drift correction. So you measure the beam current before and after the map. Yeah, so that's how you get it, 100 nanoamps here, and then 1 second. Yeah, so 1,000 milliseconds. So that was, that's a pretty long map.
Yeah,
It's
but
128.
yeah, it really depends on the material, the element, what exactly, like what X-ray line on what spectrometer. I get like similar low detection limits with faster maps, but just like in spot analysis, you get more counts out of a metal, you get more counts on a TAP. So it's unfortunately that's why the answer always is it depends, but
Yeah,
you can calculate what count times you can get as long as you know like how much X-rays are like in a spot.
mm-hmm. Radek says he actually needs 3 seconds to get an accurate measure absorbed current.
Yeah, it's I think there's really uh, the machines are really great. There's really nothing that I would like say there's a problem, but it's always good to know your own instrument. Just a lot of people, specifically faculty, rand, don't really know how much it sometimes takes to make sure that everything is working well and doing well. And we talk about very advanced specific, we're really pushing the boundaries things here. So I mean it's probably not needed if you do like routine analysis of Big Ten. But if you really push things and track and monitor, and that's something that I really appreciate, just that the software keeps all these records and I can look at it after the fact. I find like certain idiosyncrasies here and there where again, like, oh, sometimes it does that. And oh, if I run it in this mode and I
I think
so
that's, I'm just going to show
yeah,
something really quick for people, because I think this is actually maybe the best feature in the software is the fact that it saves everything you do.
yeah.
And so if you want to reprocess data, offline, that's great, So yeah, I guess I'll just go to, just trying to think if it matters, but I just open up a file.
But yeah, and you can
And
export it all into Excel spreadsheets and whatnot. So oftentimes it's
yeah,
like you can just export it all and just look at it.
so here's a peaking scan I did,
Yeah,
and I tuned up the chromium, So I got
yeah,
that record, and I can
yeah.
see that I adjusted it from the maxima fit, manually, and then here's the PHA scan on the chromium, and here's the iron. You can see the KF1, KF2. So I mean, having a record of everything you did that's saved automatically, and the only thing that's not saved automatically, of course, are the images. But the backscatter secondary images, because those can need adjustment and stuff like that. But it will remind you if you did forget to save it. So that's good. So when will we get automated PHA scan peak maxima saved into the setup?
I don't know what the
I don't know what that means.
you if you want to use peak maxima automatically as the you that's something that you can just check.
You can put that.
Oh, PHA. Yes, 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 yes. Yeah.
What does
Yeah,
that
that
mean?
could be. When you run a PHA scan and the peak is elsewhere, I currently I have to write down the number and enter it in the PHA dialog. Whereas if I run a spectrometer scan, I can in the dialog just with a right mouse click record the new value into the setup.
Yeah, but if you just select the maximum of the PHA, that doesn't help you, because you still need to adjust the gain or the bias. I mean, you haven't.
Well, I think the idea is that yes, for the but if you run a voltage scan, a bias scan instead of
A bias scan.
yeah, and
Oh,
I think that's
oh,
probably more the JOL people talking
I see.
maybe than the Kamikas, but
Okay.
it's yeah
Yeah,
for us.
but you can pick the voltage that you need to get the proportional response just off the graph and just type it in.
Oh yeah. No.
Yeah.
It's
Yeah.
just like us being more and
Oh,
more
he wants to have
demanding
a
and
mouse
being
click instead of.
lazier.
I see. I see. I've made people so lazy.
It is.
It's just terrible.
We're now the spoiled brats, but yes, it would be
Uh,
nice. I actually do agree. But
okay, well, put it in the wish list, Radek, on the forum, and I'll try to get to that. Okay, that's funny. I should have known. But early on in the software, I used to say, in only 3 clicks you can do this, or 2 clicks, or and it was kind of because we're working fast. Although sometimes people can work too fast, and I had a user contact me with a problem they had. And they couldn't figure out what was going wrong, and they'd clicked the wrong checkbox because they were working so quickly. So it's okay to slow
yeah, I
down. It's
know.
okay to be relaxed. It's okay. We can. All right.
Good. Okay.
Are we done?
So we're already over time as always.
Yeah.
And also because of me. But yeah, I would say we hereby conclude this webinar. Thanks for everyone joining us. And we know that it's still, despite the lengthier format for these, it's still very fast and complicated. Again, I would point to the user forum where people can ask questions, but there are certain aspects already like shown for with tutorials and all that. And then I don't know, they're like you can also have like specific shorter one-on-one trainings remotely with a specialist. That probably will be the best way if you really, really want to get comfortable with a certain specialized advanced function and you don't feel that there is enough documentation already available. But yeah, thanks everyone for coming. There will be more webinars. This one will also be on the YouTube channel, so you can revisit it and otherwise post things to the forum, ask question, ask for added software options just like this, show examples if you used the function and applied it and really helped it. Post it on the forum as well. It's a great place to have some little nerdy interaction with other people, and it always helps me and other people to just see what other people do.
And just to remind people, if you go to the forum and you haven't been there in a while, you should go every day. But if you skip a day or two, you can click here, right here, this most recent posts on the forum.
Sorry.
Or Annette, she's recovering from a cold.
Yeah, sorry, I was really, really sick. I'm still.
But this recent post on the forum is a great place to go, and then it will list in chronological order the most recent post. I just posted something on the Dwayne Hunt limit today, which is pretty interesting, I think. That's why we can't rely on the Dwayne Hunt limit for
and if you have a login, like this is available even if you don't have a login, so that's nice. But if you have a login, there's also an option to show unread posts. And so
right.
If you haven't been there for a long time, it's also a good way to catch up on whatever happened recently. And then the last thing that sometimes people, I think, get confused with a search over the forum, it always search on the level that you're at. So if you want to search across the entire forum, you need to be at the top level to put it in. So don't go into a specific topic and then say, oh, I want to now find out about something completely unrelated, because it will return there's like nothing with that keyword.
Yeah. But if you want to restrict your question, your
likewise,
search,
exactly.
So
likewise,
if you know that the answer is in ProPrePMA, go to ProPrePMA and then type in the search here. Yeah, exactly.
Good. Okay.
All right.
Well, thanks and have a great day, and see you next time.
Thank you, Annette, so much. Bye-bye.